All right, let's keep moving on in Chapter 3, looking at polynomial functions and their graphs. So first section of Chapter 3 was dealing a lot with our parabolas. I'm talking about max, mins, and such, and where that vertex is and where I can find it at x equaling negative b over 2a. But now we're going to go into polynomial functions that have a higher degree than what we saw with quadratics. So we're going to look at cubes to the 4th, to the 5th, to the 6th power, etc. So let's first look at a definition of a polynomial function. And we are going to let n be a non-negative integer. Non-negative integer would mean that it would be a positive, and it would have to be like a whole number, basically 1, 2, 3, 4. And let a sub n minus 1, all to a sub 2, a sub 1, and a sub 0 be real numbers such that a sub n, all of those are not equal to 0. I know that looks a little bit weird with that notation, but basically we're just now going to be looking at numbers that are in front of our x's of a function that is defined as this. F of x is equal to a sub n times x to the n. Add to that a sub n minus 1, which would be the next, just a new number, times x to the n minus 1. Well, if this is n and this is n minus 1, this is 1 less than what we started with. So if this is a cube, this would be a square, then we would have a first, etc. And we continue on until I get a sub 2x squared plus a sub 1x with a power of 1 that I'm not going to write, and a sub 0, which is our constant number. And this is what we call a polynomial function of degree n. Okay, and the number a sub n, which is this guy in front of the highest power, that is the coefficient of the variable to the highest power, is called the leading coefficient. So if you write it in descending order, starting with your highest down to your lowest, which include the constant at the end, then whatever number is in front is what we refer to as the leading coefficient. Now, that is important for multiple things. Looking at the way the graph is orientated, it also brings into the account some horizontal asymptotes that we'll see later on and such. But actually, that wouldn't be with polynomial functions. Excuse me on that. But the leading coefficient will help us with some graphing pieces. So, what does it mean to be a polynomial function, or what does one look like? I'm going to give you some examples here, and then we're going to kind of look at what it means graphically. So if I just have negative 3x squared plus 4x minus 5, that would be a polynomial function. I could also look at like negative 4x to the 4th plus the square root of 3 times x cubed minus 2x plus 3. And then f of x equals negative 8x squared times the quantity of x squared minus 2 times an x plus 4. So I can kind of just write it as factors, and that there also would be a polynomial function. Now, notice that we each have positive powers here with all of those that are positive integers. Doesn't matter if I have a square root here in front of this number, it still works. Excuse me. Awfully nice if I have just an integer in front of there, but it's okay to have these rational numbers. Now, what would a polynomial function, or not a polynomial function, look like? If I said g of x is equal to negative 3 square roots of x plus the square root of 2x squared minus 2 or something like that. The problem with this equation is this guy right here. You cannot have a radical that has a variable underneath it in order for it to be a polynomial function. Another one would be something like negative 2 over x cubed plus 4x squared minus the square root of 5x plus 2, something like that. And the problem on this one is not this guy right here with the square root. It's okay to have a number, but not okay to have a variable. The problem with this one is this guy right here, where you can't have a fraction within there. Remember, they have to be positive powers and all integers with that. Okay? Now, graphically, for polynomial functions, the graphs of polynomial functions of degree 2 or higher have graphs that are smooth and what we call in math continuous. When you get into calculus and such, continuous is a huge concept within there. And so smooth means that the graph contains only rounded curves, we should say, with no sharp corners. Okay? Sometimes we refer to those in calculus as pointy points. Okay? So no pointy points. Continuous means that the graphs have no breaks in the graph and can be drawn without lifting your pencil from the rectangular coordinate system, basically, okay? So if I look at just some examples, if I have something that looks like this, I'm not going to draw the coordinate plane because I think that makes it a lot confusing. That would be a polynomial function. It's nice and smooth. There's no points. I can draw it with just one line without picking my pencil up. I could also do something like this. That would be a polynomial function as well. Now, what would not be a polynomial function is if I end up having something that looks like this, and then I jump here and I go in that direction, let's say. Because I have that break, that would not be continuous, okay? That is not a polynomial function. And something like this, where I have kind of a point, and maybe I kind of do something like that. Because of these points, that guy right there, and this guy right here. Those are our sharp points. That would eliminate that from being a polynomial graph. Okay? So in this section, we're actually going to graph some of these, but there's all kinds of characteristics that we have to have in order to do that. Okay? There are many patterns that come along with when looking at these higher order polynomial functions. One of those happens to be with the end behavior. Now, what do I talk about when I say the end behavior? It's this part here. What's happening at the end of that function, okay? Is it going up? Is it going down? And do I start down and go up, or do I start up and go down, and all that kind of stuff? And we can do that and figure that out just by the degree of the polynomial and the leading coefficient. Now, as a reminder, the degree is the highest power. So if you need to write that on there, make sure that you do that. The degree of the polynomial is the highest power. So hence we have this leading coefficient test, okay, that's going to tell us what kind of end behavior that I have with our polynomial function. So as x increases or decreases without bound, that means when it goes on forever and ever and ever. The graph of a polynomial function, let's remind ourselves what that looks like from above. A sub n x to the n plus a sub n minus 1 x to the n minus 1 plus, continue on where I get a sub 2 x squared plus a sub 1 x plus a sub 0, where the graph of that function eventually rises or it falls. Now, we need to remember that n is the degree, here I alluded to the highest power, of the polynomial, and a sub n is the leading coefficient. So in order to use this test, we have to know the highest power, and we also have to know what is the leading coefficient, okay? Now, I'm going to have 4 scenarios here, and it's all going to determine on the degree being odd or even, and if our a sub n, our leading coefficient, is positive or negative. So we're going to start off when n is odd, and my leading coefficient is greater than 0. So my a sub n is positive, okay? You may want to write that down. The end behavior for our graph is going to do something like this. You're going to, if you remember the graph of x cubed, this is what you want to remember. If a is positive and n is odd, then it's going to end up coming, it's going to be rising, or actually falling to the left, and then it's going to kind of jump around maybe inside here, but in the end, it's going to go up. Okay, so for the left end behavior, it falls. For the right end behavior, it rises. It goes up. Okay? All right, so some of your exercises will be, given this function, what's going to happen on the end behavior? Does it fall to the left or does it rise to the left? Does it fall to the right or does it rise to the right? Okay. Now, if n is odd and a sub n is less than 0, so now we have a negative leading coefficient. So what's going to happen is now it's going to kind of do the reverse of that. When I had a negative in front of a parabola, what did it do? Here was my positive version. The negative ended up reflecting over the x. So basically we're going to flip-flop these. So it's going to end up starting as it rises to the left. Then inside here it's going to change, but in the end it's going to fall to the right. Okay? So on the left we are going to rise. And on the right, we are going to fall. Okay? All right, very good. Now, let's look at when n is even. Okay, when n is even and a sub n is greater than 0. So I'm looking when a sub n is positive. Maybe you want to write it that way. Okay, what's going to happen with our n behavior on the left? It's going to be rising as you go to the left. And then it's going to kind of do all kinds of little work in here. And then it's going to end up rising as well to the right. So these two over here, when it's odd, go in opposite direction. These on the evens are going to go in the same direction. So on the left, we're going to rise. And on the right, we are going to rise as well. Okay? And our last one is if n is even and a sub n is less than 0. So here a sub n is negative. That leading coefficient is negative. What's going to happen is we're again going to reflect that. Just like what happens here with our x squared. It rises and rises. Now it falls and falls. Okay, so we are going to end up having, starting here, it's going to fall to the left, going down. Then it would end up doing some kind of different behavior. And then we're going to end up falling to the right as well. So the left we're going to fall, and the right we are going to fall. Now, here's a trick to remembering this. When you, hopefully you are familiar with y equals x squared. For the even powers, think y equals x squared. That's the most basic even power. And so if you are familiar with y equaling x squared, you should know that it is a parabolic shape where we end up having that if a sub n is positive. And then in the opposite direction if a sub n is negative. Okay? Now, you also, on this side, when we have the even power, the even degree, what I want you to think about is our y equaling x cubed. Now, we have not done as many x cubes as we have with our, it's supposed to be a y, okay? We haven't done as many x cubes as we have x squareds, but here, if you want to think y equaling x cubed, it's like that little squiggle. Okay, we're going to have that squiggle that looks like that. And this is when a sub n is positive. And then our squiggle ends up doing something like this when a sub n is negative. Okay, so maybe that'll help you out a little bit with those. So this, we're going to now kind of practice some of those. So on the back side of the front page, sorry, it didn't lead it to where I could squeeze these on the front page, so we might have to flip back and forth. We have the leading coefficient test that we need to use to determine the end behavior of the graph. So we need to know what happens on the left and what happens on the right. What happens on the left and what happens on the right. Your answers are going to be rises or falls, okay? Now, what we need to know is what our leading coefficient is and what our degree is. So the degree here on this one, the highest power is that 3. It is odd. That's what we need to know, okay? And then our leading coefficient is the number in front of the highest power, and that leading coefficient is positive. We don't really care what the number is right now. We just want to know what the sign of that number is. So if we go back here where I have an odd power with an a being positive, an odd power with an a being positive, an odd degree a being positive, my end behavior, think of that x cubed, then it's going to fall to the left and rise to the right. So on the left it's going to fall, on the right it is going to rise. So it's going to end up doing something like that for x cubed. Okay? Now, if I have x to the fourth, and that's the degree of this one, so the degree here, highest power is 4, which is even, and we end up having a leading coefficient that is a -1. I don't care about the 1. All I really want to know is that it's negative. So if I have a degree of 4, it's even. Remember, think about x squared. X squared looks like this if that is positive. It looks like this if it is negative. So it's going to end up kind of doing something like this with some things bouncing around in between because it is an x to the fourth. But we just want to know about that end behavior. So to the left it falls, and to the right it falls as well. Okay. Now the next one, when I don't have everything multiplied out, it's a little bit tricky because you have to make sure you determine your degree here according to the powers that I have, okay? So please make sure that you account for that. So the degree here is a 2, a 3, and a 1. So if I multiply this out, I'm going to get an x cubed. If I multiply this, I have one of those x's, and then I have 2 out front. So 2 plus 3 is 5, plus 1 is 6. That is an even power. And my leading coefficient, this one, is going to be positive. It's going to be a positive 4 this time. So if I'm even, it's acting like the x squared. And if I have a leading coefficient that is positive, it's acting like this guy right here, where to the left it rises and to the right it rises. So I'm going to write rises here and rises. And so those exercises, that's all you have to do. Okay? Because in the end, we're going to kind of mold all this together and graph one. Actually, graph a couple. All right, so an important feature of our functions also is to find where it crosses the x-axis, or what we call our zeros of our function, okay? So that's what we're going to discuss now. And we're going to say if f is a polynomial function, then the value of x for which our function f of x is equal to 0 are called zeros of f. Now, zeros are also sometimes referred to as roots, and they're also referred to as solutions. Okay? So all those three things can be interchanged. Zeros, roots, solutions. That is all where our function value equals 0. Now, those solutions of the polynomial equation f of x equals 0. Now, graphically, what does that mean? Where is the y value equal to 0? That is where we have our x-intercepts. So, x-intercepts, zeros, roots, solutions, they are all the exact same thing. So if I ask you, like in the next questions, how do we find all the zeros of that function? Basically, I want to know when that function value equals 0. So where's my function equal to 0? That's what we're looking for. And so we have a polynomial equal to 0. Go back into, I think, chapter 1, where we were actually, or maybe it was chapter P, where we were actually solving for those equations. And in order to do that, you must factor, okay? So please make sure that you know how to do that. That's why that P.5 section is so important. So here I have 1, 2, 3, 4 terms. So in order to factor that, that is my grouping of 2 by 2. So I need to find what is common in these first two parts. Well, I have a common x squared, and when I take that out, I'm left with an x plus a 2. And when I look at these two terms, there's a 4 in common, but there's also a negative in common. So I'm going to go ahead and take out that negative 4, which is going to change each one of these to a positive. Negative 4 times x gives me a negative 4x, and a negative 4 times a positive 2 gives me that negative 8. Now, we're not finished, because now with this term and this term, we have a common expression. So I'm going to take out that x plus 2, and I'm left with an x squared minus 4. Now, the thing about it is, this has a power of 1, so I can't go further, but this has a power of 2. So I'd have to ask myself, can I go further with that x squared minus 4? And I hope you recognize that by now, that that is one of those difference of squares. So I'm going to rewrite this one. this guy is going to be factored into two binomials that are exactly the same except for the sign. So one has to be a plus, one has to be a minus. What did I square to get that? Was an x and an x. What do I square to get this? It is a 2 and a 2. Now notice here, I actually have a couple that are exactly the same. And when we're actually graphing these polynomial functions, it's going to be to our benefit, which you will see later on in the next section, why it would be nice to write it as x plus 2 quantities squared, okay? But you don't have to answer this question, because I could just go down the line and say what makes that 0, what makes that 0, what makes that 0. So in our case, here, what makes this 0 is a -2, and it is what we refer to as a double root. And what makes this one 0 would be a +2, therefore -2 and +2 would be my zeros, would be my answers for that polynomial. Okay, let's try another one. If I want to know where the zeros are, I want to know where that's equal to 0. That's what we need to find out. So this one actually has just two terms. So we first have to look at the first rule of factoring, which is to take out any common terms. Notice each of them have an x squared. So I'm going to take an x squared out, and I'm left with an x squared minus 4. Maybe I should have changed the number, because that gets me right back to where I had over here, where I end up having to factor that as the difference of squares. So x plus 2 times an x minus 2, and all that's equal to 0. Now, can't do anything more with this square term. Each one of these have power of 1, so we're done factoring. So I need to go down the line and now say, okay, what makes those 0? What makes this guy 0? Don't make it too hard. It is 0, and because I have a power of 2, that one is a double root. It occurs twice. And then this one would be -2, and this guy here would be +2. So 0, -2, and +2 are the zeros for that function. Okay? All right, so first we had the leading coefficient test to kind of give us our end behavior. Now we found the zeros of our polynomial function. And next we're going to talk about the multiplicity of these zeros, okay? So this just determines kind of some characteristics on my graph whenever I'm going to be putting this all together, okay? So the multiplicity of zeros, the number of times a 0 occurs, for instance, remember this one was a double root, it occurred twice, this one occurred one time, occurs is important for the behavior of the function graphically. This is referred to as the multiplicity of the 0. Basically, the multiplicity of the 0 is the power of each factor. So here, this one occurred twice. That multiplicity is equal to 2. This one occurs once. Its multiplicity is equal to 1. Now, it is determined upon the graphic part of our characteristic here, whether or not the multiplicity is even or whether it is odd. So for odd multiplicity, we're going to have something. And for even multiplicity, we're going to have something. And let's kind of, I need to cross that 0 out. It needs to come over here. Little editing problem, sorry. Okay, so let's talk about odd first, okay? If we have an odd power of our root, then the graph is going to cross, or the graph crosses the x-axis at that 0. So it's going to go through the axis, okay? But if I have an even multiplicity, so where this double root is, where this double root is, or if I have a power of 4, power of 6, whatever the case may be, the graph bounces off of the x-axis at that 0. So it comes down and it touches that axis, but it goes right back off, okay? So what does that look like graphically? If I say I have 3 zeros on this function, and they have multiplicity, all odd multiplicities, then what's going to happen is I'm going to come through, cross through, and cross through. So these are all odd multiplicities. Okay, so if I have an even multiplicity, so maybe I have 3 zeros, okay? And here, I'm going to come from here, make this kind of come through and bounce. I'm going to cross through on this one, and then I'm going to bounce at this one, okay? So here, This one is an even multiplicity because it comes through and bounces off. This is an even multiplicity, and because this one crosses through the axis, this is actually an odd multiplicity. Okay, so make sure that you recognize that. And that's going to be very, very helpful for us to know when we get ready to graph one of these big functions. And it's actually not too bad once you kind of put it all together. All right, so we're going to find the zeros of these functions, and we're going to give the multiplicity, and then we're going to state, does it cross or does it touch or bounce off of the x-axis for our zero, okay? So for our zeros, basically we do exactly what we had talked about before. We go through and we say, okay, what makes that 0? What makes that 0? What makes that 0? Unfortunately, -4 will never equal 0, so it's never going to give us a 0. But what number plus 1 is 0? It is -1. What number minus 5 is 0? It is +5. So those are our two zeros. Now, let's talk about the multiplicity. The multiplicity of our 0 at -1, look at the power. The power is 2, so it is even, okay? So, maybe I should undo that. Let me put, the multiplicity is technically 2, and then or underneath here, I'm going to remind us that that is an even number. And so if that is an even number, what happens when we have an even multiplicity? That's this guy over here. Our graph bounces off of the x-axis, or it just touches, is what these directions say. That's probably what the book refers to it. I put the bounce in. So it just touches the x-axis, okay? Looking at my 0 of 5, the multiplicity is the power of that root. So the multiplicity is 3. It is an odd number. So for odd numbers, what happens to our x-axis at that 0? It ends up crossing through the x-axis. Okay, let's turn to this next one. It's already nice and factored for us, so we don't have to worry about doing that. But I'm going to go through and figure out what makes each one of those 0. What makes this 0? What number squared is 0? Well, it is 0. Don't make that one too hard. What number minus 3 is 0? It is 3. And what number plus 4 is 0? And it would be a -4. So I'm now going to look at each one of those multiplicities, and it's going to end up determining what kind of thing happens at that 0. So if I look at 0, the multiplicity of it is equal to 2. That is an even number, therefore it comes through and it bounces or it touches that x-axis, but does not go through. When I have the power, or the 0, factor of 0 where the 3 comes from, x minus 3, look at its power, the multiplicity is 3. It is odd, therefore that is going to cross through, that function is going to cross at that 0 through the axis. Then I look at this factor of x plus 4. I don't see a power. Remember, it is an invisible 1, so its multiplicity is 1. That is an odd number, so therefore, at that root, or that 0, it would also cross at that point as well. Okay? All right, very good. So, let's now talk about an important theorem. It's pretty self-explanatory, but sometimes this is helpful in making sure that we know that there's a 0 at a certain spot or in a certain interval, and it's what we call the intermediate value theorem. So I'm going to let f be a polynomial with real coefficients. If f of a, that's the y value when x equals a, and f of b, that's the y value when x equals b, have opposite signs, so one's a plus and one's a minus, then there is at least one value of c between a and b, for which the function value at c equals 0. Okay, and we'll look at this graphically here in just a second. Equivalently, the equation f of x equals 0 has at least one real root that happens between a and b. Okay, so that's what it means, basically. That if we have our function equal to 0, there is one root that crosses through between a and b. So graphically, this is what this means. If I throw this coordinate system on here, and I have a function that goes up, let's say, like that, okay? I'm going to let a be here. I'm going to let b be here. So there's my interval from a to b. I'm coming down on this function. Here is this point, at A. Therefore, that means over here, this is f of A. And f of A is down in the negatives for this graph. If I find the point here at B, I'm going to come over here, and this is going to be f of B. So that's the y value that corresponds with my x equaling B. Now, here's my x-axis. This is my y-axis, don't forget. And so, what this intermediate value theorem says is that if f of A and f of B have opposite signs, so this one's positive, this one's negative, so they do, then there has to be some value C that's between A and B such that my function value at C equals 0. Or it crosses the or the x-axis. It's a 0, it's a root, it's a solution, it's an x-intercept. So this is where C is. Okay? So there is one real root, or one real 0, if you like to use that term. That's between A and B. Okay? So it's pretty easy, actually, to determine if this is true. So if I want to check two points or two x values to see if there is a 0 that lies on that interval, basically, I now need to look at what is f of negative 3 and what is f of negative 2. If they have opposite signs, by the intermediate value theorem, there's a 0. So we're going to look at what is f of negative 3 and what is f of negative 2. Are there opposite signs? Okay, so I'm going to take negative 3 and plug it into my function, which is 3 times negative 3 cubed minus 10 times negative 3 plus 9. So let's figure that out. Negative 3 cubed is a negative 27 times 3 is a negative 81. This becomes a plus 30 plus 9. So if I look at negative 81 plus 30 plus 9, to me, it's going to be a negative number, and that's actually a negative 42. And if I determine what is f of negative 2, I'm going to put negative 2 wherever I see the x. So that means I need to cube it, minus 10 times negative 2 plus 9. And when I do that, negative 2 cubed is negative 8 times 3 is negative 24. Then I have a plus 20 here and a plus 9. Well, this is 29 minus 24 gives me a 5. Now that's a positive 5, and that's what I really want to hone in on. This one is positive, this one is negative, so yes, show that this has a real 0 between there. So because f of negative 3 and f of negative 2 have opposite signs by the intermediate value theorem, there is a 0 between negative 3 and negative 2. Okay, so that's basically what we have there. And again, that's used whenever you're kind of graphing and you don't have a utility to graph it. A lot of times we'll have that utility, but there are ways to check it without. Okay. All right, so now let's put this all together. There are 5 different things here that they want us to look at to see if we can get a graph on this polynomial function. Okay, so we're going to use our leading coefficient test to determine the graph's end behavior. We're going to find the x-intercepts by letting y equals 0, don't forget, and state whether the graph crosses the x-axis or touches the x-axis and turns around at each intercept. So that brings in that multiplicity part. And then we're going to find our y-intercept, which means we need to let x equal 0 to do that. And then we're going to determine if our graph has any y-axis symmetry or origin symmetry. So that is evaluating f of negative x if it is the same function that you simplify it down to. That's the y-axis symmetry. If we end up getting the opposite of that function, this is a while back that we learned this, then it's going to have the origin. If neither one of those happens, then it is neither. Okay, and that's just helpful for when graphing it. All right, so part A. Let's look at the leading coefficient. If you need to turn back to the very front page, that's where this test is. We need to look at the degree, and we need to look at A, the leading coefficient. The degree here, highest power is 4, which is even. And our leading coefficient is positive. We don't really care what it is. It's just positive, okay? Is all we care about. So remember, An even power is like that x squared. And if a is positive, I end up having something that looks like that. So my end behavior is going to be like this guy right here. So on the left, we are going to rise. On the right, we are going to rise. Okay. Part B. Let's find our x-intercept. So in order to do that, just do the opposite. We want to let y equal 0 or our function value equal 0. So we want to know when x to the 4th minus 8x squared plus 16 equals 0. And this is where a lot of the math is going to come into play because I have to factor that. So when I factor that, it is a trinomial. So there is a plus at the end, so they are the same that match the first. I'm going to split up x to the 4th, so this time I get an x squared in each of those, and then what do I multiply to get 16 that I add to get 8? And unfortunately, that one's not too bad. We multiply 4 times 4 to get 16, and add 4 and 4 to get 8. So now we end up having this x squared minus 4 twice, but it can actually factor. Don't forget that's one of those differences squares. We've seen it twice in this lesson. So I'm going to run it down here. For 2 here, these first 2 come from here. These second 2 come from here. Now in the end, what happens is that I end up having both of those 2 factors occurring twice. So this is where we have to determine our zeros. We have to determine the multiplicity and what happens. Does it cross or does it touch the x-axis? So what makes that 0 would be -2. Its multiplicity equals 2, which is even. Therefore, since it's even, go back on the back of the first page, it is going to touch the x-axis at that 0. And if I ask what makes that 0, it would be at 2. Its multiplicity is also 2 as well, which is even. And so it will actually also touch at that 0 as well. Okay? All right, now, that's part B. Part C, we need to find the y-intercept. So we're going to let x equal 0. What does y equal if x equals 0? I get 0 to the 4th minus 8 times 0 squared plus 16. And this is the easiest of the two because this term goes away, that term goes away, leaving me with the y-intercept of 16. Okay? And for the last one, we need to determine the symmetry. So we need to look at what is f of -x, and hopefully I will get back the original, or I will get back the opposite, so I know that it has y-axis symmetry or origin symmetry. So I'm going to take -x, and I'm going to plug it right in here wherever I see an x. So -x to the 4th minus 8 times -x squared plus 16. Okay? Now, when I do that, here, this is going to end up negative times negative times negative times negative, ends up as a positive x to the 4th. And a negative x squared gives me a positive x squared times this negative 8 is still a minus 8x squared plus 16, which if you compare that to the original, that is the original function. And so, I'm coming up to this part here where it says that I have a y-axis symmetry. Okay, it's my mirror over that y-axis. Okay, so let's kind of put all that together, and I'm not going to be, we're going to have to do my lab math, so hopefully they kind of ask you to kind of look at, oops, I'm going to undo that, because I have a y-intercept of 16, so that's way up there. Okay, so you may just have to recognize the graphs, or they may ask you to actually graph some of them on your own. So I'm going to put, I know that my left behavior, it rises to the left and it rises to the right. I also have zeros at -2 and +2. I also have a y-intercept at 16. I also know that here at these zeros at -2 and +2, we're going to come from our end behavior that's rising to the left. I'm just going to touch at that 0, come back up to this intercept, touch down here, and go back. So if we end up having that all in it, we also have our y-axis symmetry. So I know I have to be symmetrical over the y-axis. So this is our sketch that we're going to do. So we're rising to the left. So I'm going to end up kind of coming down here. I have to touch that 0. I have to come up through this intercept. I have to come back and touch that 0 and come back up for my end behavior to be rising on the right as well. So it kind of looks like a W, okay, when we have that. So that would be an x to the 4th equation that we have. So basically just kind of molding it and putting it all together in one problem, okay? All right, I'm going to change colors because I've kind of merged into the other space here. And we are going to look at this one. F of x is equal to negative 3x cubed times an x minus 1 squared times an x plus 3 quantity squared, okay? So for part A, we need to know the degree. The degree comes now, this is all factored, which is nice for part B. But here we have to count our powers. So we have 3 here, 4, 5, 6, 7. So our degree is 7, and it is odd. Don't forget. That is important. And our leading coefficient this time is negative, okay? So if our leading coefficient is negative and we have an odd power, remember x cubed kind of looks something like this. It was a little squiggle. And if it was negative, it rose to the left and fell to the right. So that's kind of what our end behavior is going to be. On the left, we are going to rise. On the right, we are going to fall. They are opposites of each other, okay? All right, now what is going to be our zeros for part B? For part B, I now need to set this equal to 0, and I'm not even actually going to just rewrite it because I already have it there. So let's just write out what our zeros are. It's completely factored, so I don't have to do anything to it. So what makes this guy 0? If it's just an x out front, we do have a 0. The multiplicity of that is going to be the power, okay, so it is a 3, which is odd. If it's odd, then we are going to cross through that 0. If I now look at this multiplicity, we have, actually this has a 0 of 1, but the multiplicity equals 2 here because that's the power. And since that multiplicity is even, that is where we are going to, whoops, I was going to write cross, but we don't cross at that point. We actually touch. On an even power, we will touch at that 0. Therefore, here at negative 3, we will have the same as what's happening at 1. Multiplicity equals 2, and so we are going to touch. I'm going to keep writing cross, but we're going to touch at that 0. Okay. All right, so part C. Part C, we need to know what the y-intercept is. I'm going to do part C down here. If I want to know the y-intercept, I need to let x equal 0 for each one of those. So I get negative 3 times 0 cubed, 0 minus 1 squared, and a 0 plus 3 squared. And so, notice, I don't really care what the other ones are here at the end, because if I worry about this, this is going to be a 9, this is going to be a 1, so 9 times 1 is 9, but the minute I get here to the 0 cubed and times that by 0, the whole thing is 0. So we have a y-intercept of 0, and then we are going, which is also an x-intercept, hence, and then part D, we are determining if we end up having a y or a symmetry, okay? So if I look at, let's see if I can squeeze that in here. I don't have much room on the left or on the right there. If I put negative x into my function, what I get is negative 3 times negative x cubed, and then a negative x minus 1 squared, and a negative x plus 3 squared. And I have to make sense of all of this. Now, this here, whenever I look at this negative x to the 3rd power right here, that's going to end up a negative times a negative times a negative is going to be a negative x cubed. Times this is going to give me a positive 3x cubed. Okay? But when I talk about this and I try to take away this negative that's in front of these x's, when I take a negative out, I'm going to be left with an x plus 1, okay, which actually completely changes that base or that factor right there. So we want to make sure no matter what I do, if I take each one of those out and square it, I'm never going to get back to the original. I'm not even going to get back to the opposite of the original, okay? So I didn't completely finish that out, but logically, we're looking at this, and that's going to be neither on our symmetry. It's not going to have y-axis or origin symmetry. Okay, so let's put all this together. I'm going to scroll down a little bit so that we can do a graph, okay? I'm going to have in behavior that goes up on the left and down on the right. So we're going to go up, then we're going to do some stuff in here, and we're going to go down, okay? So we're going to have zeros at 0, 1, and negative 3. So I'm going to put those on there. 0, 1, and negative 3. I'm going to put a dot right there and a dot over here on this one. Okay? Now, let's remind ourselves what happens. We are going to be rising to the left. So it's going to rise here. So in a sense, we're going to kind of come down. At negative 3, it just touches that axis. So we're going to touch that axis. And then what happens at 0? At 0, it's going to cross through our axis. So we're going to touch, and we're going to come back up, and we're going to cross through. But at my 1, it's a multiplicity of 2, which then touches that axis. So we're going to come down so far, come up and touch, and go back the opposite direction for our end behavior that falls to the right. So again, that's just a sketch. We could actually, if we wanted to, look at like 1/2, plug 1/2 into the function, see what you get. Plug -1, -2 into the function to see how high that you can get. And you can do that, but we're just looking at sketches here on that. Okay? All right, so I know that's a long lesson, but there's a lot of good stuff in there whenever we're looking at analyzing graphs and creating those polynomial functions. So from here, in the next section that we do, it's going to be talking about rational functions and graphing those, and I believe that's almost close to all the graphing that we'll do. Enough for chapter 3 anyway. So until next time.